Good evening, everyone, and welcome to another vBrownBag webinar. Tonight, we're going to be talking with Earl Dodd, covering an introduction to HPC, or high performance computing in the cloud. Earl is a worldwide technology global HPC business leader for HPC. How's it going, Earl?
It's going great. Glad to be here, and I'm excited.
Awesome. We're excited too. So Earl provides HPC and supercomputing strategy, technology enablement, business development, marketing, and sales support to World Wide Technologyâ, global enterprises, and governments. He helps to achieve customers' desired return on investment by leveraging HPC technology, extreme data in motion, and the cloud, utilizing secure ultra-scale architectures and collaboration environments. Earl has over 43 years of experience in HPC and supercomputing and has helped and led commercial enterprises, professional organizations, and government positions. Earl also is a frequent speaker and expert panelist at national and international trade shows and a big sci-fi fan. Is that right?
Yeah, that's right. If I can get into orbit, that would be awesome.
Yeah, that's that Mars.
Yeah, I was kind of miffed at Mars 1 fell through. I couldn't
right.
get my one-way ticket to Mars. So,
well, I am a big fan of sci-fi myself. Love reading sci-fi books. I don't know if you've watched The Expanse, but that was a great, fun show recently.
I lived that, right? That in my head, at least.
So. Right. So before we get started, just a few housekeeping notes here. If you want to get in on the conversation, hopefully you're joining us live. You can ask questions directly here. If not, you can always ask questions or post them on Twitter. We'll be watching that throughout the night. You can follow Earl at HPC Beacon. You can follow me at Cloud Osmotic on Twitter. And yeah, really happy for everybody to join. And thank you for your time. And Earl, we'll turn it over to you.
Oh, fantastic. Thanks. Well, buckle up, folks. Here we go. So, see my slide?
We can.
Okay, so I do appreciate that a little bit, what we're going to go through. Boy, Sean already did the introduction, so I probably don't have to do much there. I have always felt that it's necessary when I talk to mere mortals like ourselves, what actually is high performance computing, and kind of destroy some of those myths that are around HPC and what it is, kind of tie that in to the cloud, the HPC cloud. And I think it's important. I got a few marketing slides that show you that why the HPC cloud is here today and why it makes a lot of sense. I have a real use case. I believe I've redacted everything there that is customer specific. I'll go through also some of the RFP discussions. I'll just read that. I don't have them on a slide just in case this gets somewhere else out there. And then just follow it up with some next steps, basically a conclusion or summary, and ask questions. You know, everything is on the table. There's no such thing as a dumb question. Just keep asking. Again, who am I? Just a little bit. Yes, I've got 43 years of experience. I have probably done every stupid thing with a supercomputer on the planet. I've broken it. I've shut it off when it was running for national technical means. It's just, I have seen it all. And what's very interesting is some of you may not be this old as me, but this is like 1975, 1980s all over again. It is the wild, wild west in information technology, especially in the extreme scale world, the HPC world. I helped put in the first, terascale systems with Cray, petascale systems with IBM, and hoping now you'll see the announcement on the exascale systems from HPE. So it's just a fun time out there. So let's dig into really what's HPC. And by the way, contrary to popular belief, it is not high performance comedy, although I do have a stand-up routine, but that's a different podcast, okay? And when I first started, I'm a mining engineer by background. I got a couple degrees in mining engineering. And so my whole thing was about blowing stuff up. So HPC, when I first started back in, the dinosaur ages, was high performance concrete. And so I've moved from high performance concrete to high performance computing. So that's quite a journey. So one of the things most people don't get, why is HPC different and really what it is? Remember, the first time I ever installed a Cray system, it's way more, this phone is way more powerful than that first Cray 1B at Los Alamos. And it's just amazing what technology does and Moore's law and things. But in a nutshell, just think of anything that is absolutely compute intensive, numerical intensive, whether it's floating point or integer capabilities. And you add tons of data to this. And most people don't realize this, but a lot of HPC and high-end supercomputing is very pixel intensive. It does you no good to suck in the data to compute something if you can't visualize a result. It just doesn't make any sense. So the key is, how do you put that all together, wrap some software around that with modeling and simulation, basically building, the new buzzword of the week is building digital twins. Well, gosh, we've been trying to build digital twins since the first time on modeling and simulation. We're getting to the point now where we can truly do that. I actually have a slide that talks about where things are going and what's needed next. But at the end of the day, what do we do with this darn stuff? We run these big computers and we get a resultant. And why is that important? So it basically gives you a competitive advantage. Most people don't realize that we're in a cold war on supercomputing right now. The race is on to whoever has the largest capability or cumulative capability for computing for national security purposes. It's all about actual collaboration and keeping these assets moving and driving situational awareness. So people, does anybody play golf? I'm terrible at golf, by the way. So I just dig up the course. That's the mining engineer in me. But golf clubs are absolutely modeled on HPC systems for, especially, carbon fiber and the swings and everything else to get that down right, all the way up to, and the golf balls, all the way up to your car, you're talking to Siri or something like that, all supercomputing. Oh, and anybody's ever seen the weather or listened to the weather? We're not quite there yet in getting the accuracy, but we are getting it. That is a supercomputer. And so most people then say, well, what's the difference between a supercomputer and HPC? Now, I grew up with Cray Research and the father of supercomputing, Seymour Cray. I worked for Seymour at Cray Research. And, he would just tell you, everything's a supercomputer, just that his is bigger, better, badder, that kind of thing. So there is a little bit of a demarcation, but I don't want to get hung up on the semantics around HPC and supercomputing. Just think of them as kind of in the same class, but within that computing class, we bust it up into two major layers. There's what's called capability computing. That's the very high end. That's the very high end. That's where we're making sure that our national nuclear stockpile is ready. Okay, it's about finding the bad guy and sifting through all the data. And then there's capability computing, or sometimes referred to as throughput computing. And that's the real big area, the big sweet spot. So if you were to take this triangle and put percentages on, maybe 10% at the top, probably closer to 8, maybe a little bit on the bottom, maybe 5, 8%, somewhere in the bottom, and the rest is the middle. And I play mostly in the sweet spot, but I have a lot of experience also in the capability computing area.
What is the RYO?
Oh, roll your own.
Roll your own.
Roll your own, you know. What is it, CBD or something now, right? You know, I got to have my own little, you know, pot plant there or something. So I got to roll my own over here. Boy, I hope that doesn't go out too bad. But so that's the way things are kind of out there. You may have heard of Beowulf clusters and things of that area. Those are kind of roll your own. The other thing that's going on is specialized. There's a cycle in industry, and it's mainly in all industries, but certainly in information technology, or if you're in any other place other than the United States, information communications technology, ICT. And so you start out with this specialization, like in my world, it was the Cray and the vector machines, right? And then you go into commoditization. So that would be the advent for like the RISC architectures and the Intel architectures, x86-64 kind of things. And then it kind of goes back over into democratization. And so democratization is all about in my opinion, a business model about the cloud. And so that we've gone through that circle around this spiral. Well, we're back into the spiral right now with specialization. So you've probably heard of things like TPU, tensor processing units, and obviously GPUs as accelerators, but there's tremendous number of systems coming out there from either Inspire Semi with their RISC-V architecture, there's Tachyon with their solution, tremendous number of specialized AI systems, neural network, and certainly this thing that's coming to fruition called quantum computing, which is a really fun time. So it's the wild, wild west out there all again. We still have democratization, we still have commoditization, now we got specialization, and it's confusing. And so my job is just simply to sift through all the sands and dirt and try to find the gold, right? Keep on using my mining metaphor. The one thing I want to make sure what most people come away with, if you wanted to put a difference with supercomputers, is supercomputers are generally co-designed. And by that, I mean a government entity like the Department of Energy works with somebody, you know, an Intel or an AMD or a Cray or somebody like that, and go towards a roadmap that's 5 to 8 years out and build capability to reach that roadmap 5 to 8 years out. That is absolutely a supercomputer. HPC, I wouldn't necessarily say is always commoditized, but it is more referenced architecture than it is with the co-design. And so I kind of basically summed this all up here. It's used across the board. HPC is, it's very common. Most people don't know about it. The other thing that happens in HPC in general, and this is not always the case, and I'll give you 2 examples for this, but in general, HPC takes the first arrows, gets it right, it breaks, sometimes it just doesn't work, gets fixed, and that technology then matures and generally goes over into the enterprise class world. Sometimes it allows it to go down into desktops and commodity workstations and things like that. But generally, it goes across into enterprise class computing. A couple examples of where that has not happened is virtualization. That is a really nasty word in HPC. I believe it's inevitable soon, within the next 5 years or so, that virtualization will come into the HPC world. We finally adopted containerization. We've had a form of that through what was called the modules capability. So that's certainly one of them. And then the other area where enterprise has led HPC has been in the area of cloud. HPC has been screaming and dragging its feet all along. I can't tell you how many excuses I've used or I've heard about why HPC just can't be in the cloud. I'm going to disprove that today, but that's an area that's very interesting to me for growth. And so what has happened now is HPC has started to blend into other, sometimes marketing statements, other capabilities out there. And some of those other capabilities is what's called high performance data analytics. You know, maybe you're doing Spark, or you're still doing Hadoop and things like that. Okay. Obviously, it includes a supercomputing capability. There's a new class of computing out there now called urgent computing. I'm not sure I like the word urgent computing, or the word urgent in there, but if you haven't heard what urgent computing is, it is extreme scale HPC that is focused on a singular outcome. And this term has evolved from the efforts of COVID-19. Most people don't realize the amount of supercomputing in the hundreds of exaflops that went in to either look for a vaccine, find molecule docking exercises, going and find, you know, who's susceptible and who's not, etc. And probably the first time in history, certainly the first time for me, I have seen where literally companies and countries have gotten together almost single-minded to help figure out what's going on with COVID. And so people say, well, geez, you know, the vaccine or whatever come out, you get on those religious debates, right? But the amount of computing power that went into that is just astronomical. How am I doing on time? What do I got? 3 or 4 days left?
Well, we have about 20 more minutes or so, but I think, you know, that's a great place, I think, to, so Rob had a question in the audience that says, you know, are we still seeing specialized chips being built for HPC or supercomputers?
Oh, absolutely.
Or is it a matter of daisy chaining, commoditized CPUs, or a mixture of both, or?
Both. It's still cluster based, or sometimes you may hear it called super clusters and super clustering, but absolutely now. First off, some groups of organizations cannot get the class of system that they want, so they're building their own. Yes, some of these guys are hyperscalers, okay? But you're seeing very much a stratification in specialty computing and AI. And let's break down AI into just ML, okay? Just machine learning and deep learning. So there's classes of computing, classes of architectures absolutely going after these things. So, you know, there's probably I wish I'd have brought that slide. There's probably about 12 or 13. Yeah, about 12 or 13 different chip manufacturers, chip architectures coming out over the period of time. Some are only to be in certain countries like India or China. They're building their own indigenous chip systems to do that. But in general, you'll be able to get any, I call it asterisk PU. We're running out of letters to put in front of, CPU, DPU, APU, IPU, XPU, TPU. Did I say that already? I can't remember. Anyway, we're running out of letters. We're probably going to go into the Greek alphabet.
Probably QPU at some point soon.
GPU.
Quantum processing.
We already have QPUs.
Right.
We already have that. And there's the religious war between quantum annealed and, universal gate theory. And we can have a debate on that one. So
Excellent.
No, this is why it's fun. Now, the deal is software lags everything. Poor software gets a black eye once again. Probably deserved. If it was me, the first thing I would do is get rid of the operating system. The operating system takes up just too much time. All I want is a hypervisor and get me right down to the bare metal. That's all I want. Some reason Red Hat is not like that idea, but we'll talk to them. Let's get on our speedometer here. I kind of mentioned the word exaflops and things like that. I'm not trying to be, tongue in cheek. Flops are a real thing. If you haven't heard about it, floating point operations per second. That is our speedometer in HPC. So if you do lots of flops, if you do a lot of floating point operations, and you can do it in a short period of time, then and I can even cluster these things up, I can do wonderful things. So today we're right in the area of this exaflop world. We're right on the cusp. We have exaflops machines. We just haven't told you about them out there. But okay, that's great. 10 to the 18th power. Well, look at some of these other problems that we're still trying to solve. Doing a full plane simulation, especially at hypersonic speeds. Oh my gosh. Lots of opportunity here for speeds and feeds. So going into the cloud, I want to make sure you understand where things are going. So in HPC, we have this thing called capability computing. So I'm looking at the National Nuclear Stockpile. I'm reading the graph model from hell, whatever it is. And then there's the capacity computing. That's what most of us mere mortals are doing. And that's classically referred to as, just traditional HPC. And sometimes you throw big data or high performance data analytics and AIs coming in here and everything else. But here's what's really taken off in the world is this thing called the edge in the cloud. And that's what most people don't realize. It's not a zero-sum game here. There's more, as I showed in the other slide before, there's tons and tons of more compute power and more storage requirements needed for these models and simulations. We are still lacking horsepower. And when we put all of this together, we call this fusion computing. And fusion computing is the fusion of HPC, AI, big data, edge, cloud, and IoT. Okay, put it all together. That's where it's going. And we're very excited about where I'm at in leading this global business practice around HPC is that this allows us to basically do new and different things with the workflows. Now, are we going to get access to a single exaflop machine instance at AWS or Azure or Google or OCI or IBM Cloud or Alibaba or Atos now, etc.? No. But we are doing so much work in the cloud to run on HPC systems on-prem. And that is starting to get really, really gray in there. So there are companies and countries just absolutely beginning in the cloud for HPC. And there's still a challenge. Don't get me wrong. There's still data locality, sucking an elephant through the straw kind of thing. That's still really tough to do. So I just want to make sure that, HPC is a big business. HPCs, you make a ton of money, and there's still a little hiccups along the way, but the key is kind of balance all of that together. Don't be one way or another. If you drew a radar diagram or Kiviat diagram or something, try to balance this all out. And I'm going to blow through these really fast. It's not a small market. Most people don't realize it. Okay, it's small compared to the bigger market. This is Hyperion research data, but $6.3 billion. I'll take that. Good growth on that. They haven't been able to size the HPC edge yet, frankly, because they haven't been able to define what the edge is. Because if you ask 4 people what edge computing is, you get 12 different answers. But other than that, but it's a big market. It's a very profitable market, contrary to popular belief. Now, where does the cloud sit in here? Man, it is growth all the way. So because of its compound average growth is so high, it's starting to catch up. Will it ever be all cloud and no on-prem or hybrid? Absolutely not. But the key is how to balance and put this together. And what is very interesting here is when we slice it and dice it, so to speak, that sounds like, some commercial on TV or something, is there are two industries, there are two verticals, there are two scientific and technical domains that are just going gaga over this. Computer-aided engineering, CAE, CAD, CAM, computational electromagnetics, computational fluid dynamics, etc., the CAE stuff, and bioscience. So as you can see, that's a pretty good chunk of change, 2, 3, 4 billion out of the whole 9 billion. So that's what I'm focused on is that top of that list.
Yeah, the biosciences is interesting. Definitely a lot of work, computational power that goes into. I mean, a very common one is folding at home, right?
Exactly.
With protein folding, you can lend your computer to help.
But we,
with that.
We help. I don't know if a lot of people realize during as urgent computing exercise, we for WWT at the ATC, we put a lot of assets into folding at home.
Oh, interesting.
Oh, yeah. Most people don't realize that. We were, what was it? We moved up to like number 17 up on the list because we just turned a lot of assets on folding at home. It's the typical WWT culture. Let's do something right for the world. So
yeah, that's fantastic.
Yeah.
So Graham had a question: is everything floating point? Why do we measure it in floating point? Why not integer? And then there's a follow-up question to that.
Yeah, I can answer that. Yeah, because floating point's hard, integer's easy. I can do integer with shifts. Floating point takes a different functional unit capability, and depending upon whether it's single precision, double precision, half precision, quad precision, it's very hard. It's harder for the machine. So we measure the hard stuff. Plus, things are still written in Fortran. Yes, I still know Fortran. And formulas, excluding crypto work and a couple of image processing work, is still mathematically done through floating point.
And yeah, that's interesting. I wonder, is there a limitation or is there optimizations? I mean, this is probably too in the weeds for this, probably a research paper, but I'm curious if there's like a limitation that's set on HPC machines to not exceed a certain amount of floating point digits, or else
Well,
it would
there's actually, you bring up a very good issue, and I wish I had another 12 days to talk about it. But the challenge with floating point right now is it's defined by IEEE. The IEEE floating point, reference reference architecture. What's a NAND, not a number. Divide by zero does this. All that kind of good stuff. Okay,
Right.
and that's needed. The problem is seismic processing needs about this much precision. But when I do reservoir simulation, I need a lot more precision. Okay, and so how do you build a general purpose machine to do that? So what people are looking at now, this started out with tensor, and activities are doing tensor flow, for example, is actually redefine or describe your own floating point system using what's called UNUM, Universal Numbering System, or POSIT, not POSIC, POSIT, the POSIT number system. So I can define a 13-bit floating point number with a big mantissa if I need it. So there's whole libraries now being created. Probably the best out there is from Stillwater Supercomputing, is to change the numerical representation. Doesn't change it inside the box yet. That's coming. But the change in numerical, and that's what the TPU does. That's what the Google TPU does, is change, allow that to change. So it's interesting because you're going to get more specialization to drive towards certain algorithms or modeling conditions.
So certain libraries support certain hardware chipsets better than others, or interlocked more to actually change that.
I didn't put it in here, but let me tell you one of the most fascinating things for me right now is I can go over to CUNY, was it Central University in New York? Okay, I'm going over to CUNY right now. And for $3,500, assuming I have the VLSI logic, I have the macros, they can go and do a nano print of a chip at 200 nanometers. Okay, we think, oh, wow, 200 nanometers, that's huge. I can get a 7 nanometer chip now and all this other stuff. Can you get a 7 nanometer? Can you get a chip for $3,400 printed? Okay, and they'll probably get down to 100 nanometers, 90 nanometers. Wasn't too long ago we were doing 90 nanometer chips.
Yeah.
Okay, think about the specialization you can get now when I print chips for the edge. It changes the whole equation. That's why I'm fat and happy. Well, I'm fat because I eat too much, but I'm still fat and happy.
I mean, there's just so much forward progress in all different industry verticals. I mean, in IT especially. I mean, the fact that you can purchase, I still remember the days of A drives and B drives, and now it's
Exactly.
Now USBs have more capacity than all of my systems that I had when I was growing up. So
absolutely, there's no such thing as a compact disc player, and so. And here's the deal: it's going to change again.
Yeah,
I don't know what it's going to change into. I mean, maybe we get chipped up and we become singular or singularity. I don't know. Biomechanoid. I mean, fighting the Cylons again. That sucks. But sorry.
No, I'm a sci-fi.
We're about out of time, aren't we?
This is good. We have about we have another 10 minutes or so here.
Oh, okay.
So we have a good little.
Okay, I just have a few more slides and talk to you. And again, I hope I redacted these well enough. If you see a customer name on there, please don't mention it. So this is a real life
We'll claim that in post-processing.
Yeah. Burr. Anyway, so has anybody ever looked at a logical diagram of an HPC system? I mean, has anybody ever walked into a computer room, and seen an HPC system? If you do, you'll think, well, geez, my enterprise class system looks that way. Okay, the mainframe looks different. Okay, but long live the mainframe. Okay, but what you probably won't, what you'll probably notice is where big systems are, big HPC systems are, is there's cabinets upon cabinets upon cabinets of this stuff. It is loud because the fans are blowing all the time because they're all running as hot and fast as they can. And like I say, it's hot. If you ever walked into the hot aisle containment, whew, sweat. Okay. So just take, this is an automotive customer. This is a real kind of solution here. I cleaned up some of the stuff, but take that left-hand rack right there, take that left-hand rack and just multiply it by 10, 20, 30, 40 racks, okay? And fill up a basketball court. Okay, that's the kind of size of systems I usually deal with, right? So you got storage over there, and you've got what are called login nodes, and that's where people come, but nobody sees the cluster because it's on a different VLAN sitting way over there, all this kind of stuff. And then over on the cluster, you got, or on the storage side, make up a number. Small systems have a few petabytes. Our large systems have exabytes of online data. What we're starting to see is a lot of memory in these machines. Until recently, it's been about 5/7 of a machine that is the cost in memory. So take this image, and now we go through magic, and I throw it onto the cloud. And this one's got a little bit of, it didn't show it there, but there were nodes in the other one to move this in. This has gone to AWS, obviously, here. And we did a lot of work. I have the RFP requirements, but they go from, we have a little bit different set of questions, right? When we talk about HPC. So sure, if it's test and dev and you've got a few things and you want to move your model over and you spin up an instance. Okay, but how many people go and get bare metal and spin up hundreds of these things, hundreds of instances, and then gang them together? And by the way, put extreme scale, commonly referred to as high performance file systems on there, like Luster or GPFS, which is now known as Spectrum Scale, even slower systems that are moderately good, BGFS and things like that. So, we had to size this, many petabytes of storage, many petaflops of compute. And what's very difficult is in some of these we have, what you may not realize is what's called DCV, desktop cloud visualization. From AWS, it was basically from NICE software. But the origination of that was my team at IBM Research. We built that. And so you think of classic VDI and graphics. Okay, hey, I can put graphics, but how do you do 3D CAD drawings interactively on the cloud and across multiple collaborators? That's really hard. You can't do that with screen scrape technology, etc. So DCV does that. RGS kind of does that. There's a couple other technology, virtual GL does that. So, you're building a whole different class of customer, a class of systems for a different customer, a different set of personas, and those have to be replicated across other domains, some in Asia Pac, some in Europe, etc. And it's not just that, it fails over. This customer does lights out. And what what that means, not lights out, but follow the sun. Excuse me, I meant follow the sun. So that, you know, the group that's working in Asia Pac gets done, it comes over to America, they work on it, goes over the PDMs, the product data management systems, and the models end up in Europe, and then it ends up back over in Asia Pac and back around. And so the data management problem of this is horrendous. So this is one implementation that we did. We basically took the previous the cluster and basically, quote, built it in the cloud. Now there's a lot of machinery around to do this. We use Altair, and this one we used Altair PBS Pro. And this one we use Univa, which is now Altair. Altair bought them. Also, Altair made it a little bit easier than PBS Pro. No wonder they bought them, because there's a lot less boxes you see over here than doing this. So this is a very, very real case of where somebody actually took the big step to they still have their own data set. Don't get me wrong. But now they're following the sun with all their teams around the world through the cloud. And this is going to be a more and more and more common use case for these folks. Were there any questions there?
Yeah, that's fantastic. So so in this scenario, then are we replicating? How does that work with the data? Is everything in US East 1? Or
No,
replicating
we
globally?
will use basic. Again, I'm not the big
Right.
HPC guy, but what we do is we create this pairing capability, and it basically will stage something, will trigger this over to that. Remember, everything starts on, because of high performance, we need Lustre. For example, in AWS, we'd use a Lustre file system. And then we drop it back over into the buckets, and that then gets replicated here for them over to EU or Asia Pac.
Okay, great. And so a question from the audience, does HPC usually and typically imply something that's data intensive or big data, or are there compute intensive workloads that run on HPC clusters that are not as data intensive?
So there are huge compute intensive, very, very light data. Crypto is one of them, right? I'm trying to break your code breaking, right? That's a very, very simple one.
Sure.
Example, another one would be, for example, reservoir simulation. Reservoir simulation doesn't have the amount of volumes, the petabytes and petabytes and petabytes of volumes of data that seismic interpretation does. And it has this whole thing called a halo effect. So it's computationally and memory intensive. What we're seeing right now is, because of the pipes are getting bigger and better and better out there, we're getting a lot more real, I'll put it in quotes, real-time processing, streaming work. We've always had that in the Department of Defense and the intelligence community and things like that. But now that's coming back for retail, things of that nature.
Excellent.
So I got just one more slide here, and I just wanted to leave you with, hey, if you're so damn excited and you want to do something, give me a holler. Get you at the ATC, the Advanced Technology Center, and we'll beam you up. Okay. there's this whole thing where HPC AI have just converged. Big data, it's over. The cloud is here to stay. HPC cloud is here to stay. I don't care what anybody else says about it. It's starting to be its own market maker. The edge is the super wild card out there. Fantastic what the edge is going to do. I think it's going to drive on-prem and cloud just dramatically. There's, like I say, urgent computing. What we demonstrated with COVID, the processing for COVID, Lord help us if something else comes along, we have the ability to marshal a lot of resources. And this is very interesting because now we're starting to build much more of these digital twins with these synthetic models that are going on. As we just mentioned, there's AI specific hardware and different chipsets out here. And oh, by the way, these things run really hot. Okay. The last big hot system I put in was 120 kilowatt in a rack. Telco runs 7, 8, 10 kilowatts in a rack. DOE specification for 2025 is 500 kilowatts per rack. There is no concept of air cooling anymore for us. Oh. It is liquid. I'm not saying water, I'm saying liquid. And that is it.
Even more call to get those next generation fusion reactors going.
Seriously, UTI, I don't know if you're familiar with the Uptime Institute, they call it the nuclear option. Data center operators, Switch, Equinix, Data Bank, Data Realty, etc. You name it, even hyperscalers are thinking, well, maybe I could just support the renuclear data initiatives and basically pull data, pull energy off of that. If I take out Bitcoin miners, depending upon whose number you look at, 4 to 6% of the world's energy is in a data center. It's consumed in a data center. Bitcoin miners raise that 2%.
I believe it. I definitely believe it. Question from the audience. You mentioned the COVID innovation and an automated use case. And recent HPC researchers have been setting new Guinness Book World Record for diagnosing rare genetic diseases and, sequencing I guess supercomputing, we all were familiar with sequencing the genome and discovering new enzymes and things of that nature. I think the latest progression of that research is health span versus lifespan and how all the different
absolutely we're getting on, instead of the diagnosis and treatment, getting on the health and prevention side.
Right. If you could predict the next bottleneck for the next 10x improvements, what would that be? Like, what's going to be what's the thing that's stopping that next level of HPC?
Software. Yeah. And most specifically around getting full utilization off of these large systems. That's why capability computing has a hard time. It's written for 1 or 2 problems, right? Run all of the assets. Capacity computing, what they do is they just logically carve up an HPC system into 1,000 way here and 1,000 way there and 100 way there and 10,000 way over here, and then throw different quote jobs at it. We need improved software. The other thing that we need is you still got to feed these beasts. As hungry as these CPUs and accelerators with GPUs and TPUs, etc., the storage, there's still storage and historical data and blah, blah, blah out there. That all has to get into the system. So we still suck an elephant through the straw. It goes around. Compute, memory, data network, compute, memory, data, network. And software is across all of them.
Yeah. Do you think that software, I mean, how am I going to phrase this? So I know a lot of software. So like, for example, Python, right? Has a TensorFlow library that you can interact to do.
Yeah, the PyTorch and everything. Yeah.
Deep neural networks, PyTorch, etc. But those are all interpreted languages. They require,
right.
They're a middleman to the CPU or the TPU or the GPU, right? And then you have the lower level machine level languages, but those are harder to, do you see,
Absolutely. We're frameworks. I think there's going to be a division or something here. But by the way, Python wins the gold medal every time, right? I mean, it's great. Here's the deal. It's like Java. It's supposed to be great. I find friends don't let friends do Java and HPC because it's interpretive language and stuff like that. It's write once, debug everywhere, that kind of stuff. But what's going to happen is these frameworks are going to mature, and there's going to be library systems underneath of that will have this open. I don't want to call out products here like open APIs, right? Open APIs that will have these accelerated libraries. Okay, they have that now. We use math libraries all the time in HPC. Whether it's running FFTs or convolutions and things like that, right? So you're going to see this intermittency getting, quote, compiled into these high performance libraries. And then the frameworks can change, but the APIs will hopefully don't change.
Right. The compile this, the more we can compile, the faster they'll run.
Yeah, it has to, because what I have a slide somewhere that shows that the actual utilization, if you take all the data centers that were measured, which was hundreds of them, hundreds and hundreds of them, the actual utilization rate is going down, and the CPU, GPU idle is going up. Which means I suck power and do no work. Partly it's feed the beast, partly it's scheduling, and partly it is I'm running interpretive stuff.
Yeah, don't keep the water running, right?
Yeah, exactly.
Yeah, if you're not using it. Well, we're running up short on time. I don't see any other questions. Earl, this was fantastic. Thank you so much. I really, really informative. Really appreciate your time spent with us today. Everybody in the audience, thank you for attending.
Yes, thank you.
And yeah, we will see everyone hopefully next week, same time for another vBrownBag. Thanks so much.
Bye.